SwayamPrabha. Digital India. Educated India.
I welcome you all to the session of thermal engineering, and in today's class we shall discuss about the first law of thermodynamics applied to both control mass and control volume systems. You know that in this course, as name suggests, we shall be discussing about the thermal engineering systems, essentially to learn the analysis, also the operational procedure of different thermal systems. So, question is, why do we need to learn all these aspects of thermal engineering systems? You know that for the human comfort, along with considering different practical applications, be it a power plant or any process industries, and as I was talking about human comfort, so air conditioning as well as refrigeration system, in all these systems, whatever processes are there, if we need to learn those processes, we need to understand about the thermodynamics, also the fluid mechanics. Now, by learning the basic things which will be applied to understand the overall performance, overall analysis of the system is very important to the designer, at least to have the optimum design of the systems. So, in this course we will be discussing about different such systems like power system, refrigeration system, along with a few mechanical systems, in which we need to apply the basic concepts of thermodynamics that we have learned from our undergraduate course. But since I will be focusing mostly on the applied part, but to understand the procedure and analysis of those applied system in a greater detail, I was thinking to discuss a little bit about the thermodynamics, basic of thermodynamics, like first law and second law. So, the combination of these two laws are important, and if we need to apply, if we need to know the, rather if we need to map the processes in different thermodynamic planes, essentially to estimate the performance of those processes, we must know the combination of first and second laws applied to different processes. So, to start with, today we shall discuss about the first law. In fact, I am not going to discuss in detail about first law, rather we shall try to recap whatever we have learned from our basic thermodynamics course. So, you know that we have learned about first law of thermodynamics. So, today we shall see that if we try to apply this first law for the control mass as well as control volume system, what would be the form of the equation and what are the different forms of the equation we shall try to establish, because these equations will be very much useful to understand the processes in different thermal systems. So, if we try to apply first law for the control mass system initially, so this is control mass system. What is control mass system? We have seen that there is no interaction of mass with the surroundings. Even if we allow that we have learned from thermodynamics course that even if we allow that a system, so if the mass in is equal to mass out, so at any time we can see that the mass is remaining fixed, but in that case identity will be changed. So, we can't call it as a control mass system. So, control mass system, that is there is no mass interaction with the system, rather between system and the surroundings. So, now if we try to apply the first law to the control mass system, we can consider a control mass system any arbitrary control mass system, lumped system. So, this is a lumped system and or lumped body, and if we have, so this is control mass system. Now, we will be applying, rather we shall try to understand if we try to apply first law to this system, what would be the equation, mathematical form of the equation. So, what we have learned from basic thermodynamics course is that first law is the statement of energy, statement of the conservation of energy to be precise. So, if we consider this is a control mass system and energy input is E in and from the system energy output is E out, then from the conservation of energy you can write that E dot in minus E dot out. So, we are trying to write this in a rate equation plus something equal to dE by dt, right. So, this is dE by dt. So, this is for system, right. So, the energy input, rate of energy at which the rate at which energy is entering into the system minus rate at which energy is leaving from the system is nothing but the change of energy within the system. Also, we need to take into account one important term, that is energy generation. There might be some ways by which energy may generate within the system, and that is why we have taken this particular term, right. Now, question is, till now we have talked about the energy change. So, if we try to write this equation for a particular process, say we are trying to apply this equation for a process in which there is no energy generation. So, right now question is, why, when we can consider that there is no energy generation? We are assuming that energy interaction with this system is only through heat and work. So, energy interaction of the system, that means energy interaction of the system with the surroundings. So, when the interaction of energy between system and surroundings is only due to the heat and work interaction, then this term can be 0. So, this is equal to 0. So, we are writing here that energy interaction between system and surroundings is only through heat and work. So, only through heat and work, that means E dot gen equal to 0. So, right, that means you know, we have understood that energy interacting in the form of heat or energy interacting between system and surroundings in the form of heat and energy interacting between system and surroundings in the form of work. If these two forms are there, then there is no energy generation. Okay. And so, this is the energy change within the system. Okay. Now, question is, so you can assume this is one assumptions, and if you also can consider that the process is cyclic process. So, the process is a cyclic process. So, I am not going to describe this because you have learned about the processes, different processes, reversible process, irreversible process, cyclic process, so many processes. So, if the process is cyclic, that means we can restore the system. I mean, if we try to give some energy input to the system, then after a certain time, maybe after having interaction with the surroundings, system can be brought back to the initial state. So, this is cyclic process. So, now you know what I am telling you, that if the process is cyclic, then this term equal to 0. So, this is using 2 and this is using 1. So, now if we try to write this generic form, we will be getting E dot in minus E dot out equal to 0. What we have discussed? We have discussed that the interaction between system and surroundings is only through heat and work. There is no other forms of energy which is either entering into the system or transferred from the system, right. So, there is, except heat and work, there is no any other forms of energy which is either entering to the system or leaving from the system. So, if that is the case, you know, we have learned from thermodynamics that in it is mostly followed that energy transfer by heat is taken positive. So, energy transfer by heat to the system is taken positive. So, let us write over here that energy transfer by heat to the system is taken positive. So, when there is heat transfer to the system, that is positive, that is the keyword. And now, if the energy is transferred from the system, following this notation it should be negative. Okay. In a similar way, we can write energy transfer by work W from the system is taken positive. So, that means if some amount of work is added to the system, it should be negative. So, following these two notations which are largely followed, you can also consider reverse, but accordingly you have to consider for rest of the analysis. Okay. So, if we try to write it, we can write that Q dot minus W dot equal to 0, right, because only energy interaction between system and surroundings is only through heat and work. So, this is the rate equation. If we try to write the total, so this is the rate form. this is in the form of rate equation. So, what will be total? So, if we integrate it over cycle over time, then we will be getting the total. So, if we try to write it, then delta cube minus delta W equal to 0. So, if we integrate it over cycle over time, then we will be getting total. So, this is the equation, and if we try to write cyclic integral del cube equal to cyclic integral del W, right. So, if we try to integrate it over cycle over time, we will be getting this equation, and this equation, which is very famous, perhaps you have studied this, you can easily identify it. So, this is first law of thermodynamics for the control mass system undergoing a cyclic process. So, starting from the generic form of the energy balance equation, we have established that the first law for a system undergoing through a cyclic process can be written in this form. Now, what we can tell from this equation, perhaps you have read, you have derived this expression in thermodynamics course. So, basically you know that this equation indicates that if we supply certain amount of heat to the system, I mean energy, but in the form of heat, the system has capability to do some work. That is what this expression tells us. So, this expression tells us that if we supply certain amount of heat to the system has the capability of doing certain amount of work. So, that is the take home message you can take from this expression. Okay. So, this is basically the expression of first law of thermodynamics applied to the control mass system undergoing the cyclic process. Let us write. So, this is the first law of thermodynamics for the control mass system undergoing through a cyclic process. I am underlining these two words, that is cyclic process. If the process is not cyclic, then what will be the form of the first law, even if we apply for the control mass system. Okay. So, this is very important, that we can write the first law even for the control mass system, but if the process is not the cyclic process. It is quite obvious that all processes will not be the cyclic process. So, if we need to write the expression, rather similar such expression for the general processes, what would be the form? So, fine. Now, we are discussing the first law for control mass system undergoing through a process which is not a cyclic process. So, this is, so essentially our objective is to derive the equation when the process is not a cyclic process. In other words, we shall take an effort to establish the first law for the control mass system when I know process is any generic general process. So, you know that if we try to say, we know, so if this is the process, if this is the control mass system and the system is changing its state from state 1 to another state 2. So, this is say state 1 to state 2. So, this is the control mass system and the system is changing its state from state 1 to state 2, but not following a cyclic process. It may be any other processes. So, if that is the case, we are trying to map that process in this thermodynamic plane. We really do not know what are the different properties x and y. It may be temperature entropy, it may be pressure volume, it may be enthalpy entropy. So, mostly in this course we need to map the processes, rather different thermodynamic processes in different thermodynamic planes. What are those planes? Pressure volume, pressure temperature, volume temperature, temperature entropy, enthalpy entropy. So, you know that I am not going to discuss in detail because you have learned it from the basic thermodynamics course, but for today, for the sake of completeness of the analysis, I am considering a plane that is x y. So, these two properties again are generic, we really do not know, maybe x is pressure, it may be volume, y may be entropy, it may be temperature, like this. So, now when the system is changing its state from 1 to 2, say it is changing state from 1 to 2 like this, and it is changing its state from 1 to 2 following this path A and coming back to the same state maybe following this path B. So, basically you know that we are, if we supply heat to the system, it will, as I told you, that it has capability to do some work. So, maybe it is again, it is changing state from 1 to 2 and again it is coming back to original state. So, now if we try to write this path process A plus B. So, for A plus B, we can write, you know, del cube 1 A to 2 A plus 2 B to 1 B equal to integral del W 1 A to 2 A plus integral del W 2 B to 1 B, right. So, that is what we are writing, right. See, it is, we know again from thermodynamics that you know this heat and work, these two are the path function. So, these two are not the property of the system, rather these are the path function. Why so? Because we have seen that delta W, if we apply, I mean for a control mass system, even if the system is control volume system, but if the process is quasi static, we can write delta W equal to P dV. It is not necessary that the system has to be only control mass system, but even if the system is control volume system and but the processes is quasi static process, then it can be written P dV, okay, a simple compressible pure substance. Now, this you understand that this work done is work done depends on pressure and volume. So, it does not depend on the state points 1 and 2, rather the path through path on which the pressure and volume changes. So, maybe the pressure changes with volume. So, now if x and y, so if this is say pressure P and if this is volume V. So, try to understand if these two properties x and y are pressure and volume, you try to understand the change in volume and pressure following path A is not equal to following path B. If that is the case, definitely work done will be different. So, this is path function, it does not depend. So, the system is starting from point 1, eventually it is coming to state point 2 and it is again coming back to original state. So, but when it is coming to original state, it is coming through path B. So, you know that if we just try to understand the area under the process line, it will give the work done PdV, right. So, you know that the change in pressure the pressure change in pressure and volume for path A is not equal to path B, and that is why these are path function. Though system is coming, system is the process is taking place between these two state points, but they are coming back following different paths. So, this is path function. Also that since these are path function, it is better to write the contour integral. So, we are writing like this. So, this is not the cyclic process, but since this is change in pressure, work and heat and work, these are path function, it is better to write in the form of contour integral. Okay. So, now we are considering, since we are trying to establish the first law applied to the generic processes, not for the cyclic processes, we are assuming fine. Now, after reaching at point 2, system is again coming back to point 1 following, let me write it using different color. System is coming following this path C. So, basically our objective is to write the first law for the generic process. So, it is now coming following path C, it is not path B. Then what we can write? So, we can write for processes A plus C, we can write 1A to 2A del cube plus 2B to 1B delta cube. I forgot to write delta cube over here. So, this is delta cube equal to 1A contour integral, because these are path function. So, 1A to 2A delta W. So, it is not 2B, again I should write it is 2C. So, it is C 2C and then 2C to 1C delta W, right. So, this is the expression. So, if we give, say this is equation number 2 and this is equation number 1. So, what we can do? We can subtract equation 1 from equation 2. Subtracting equation 1 from equation 2, we can write that, we can write what we can write? We can write that 2B to 1B del cube equal to, we can write 2B to 1B delta cube minus delta W equal to contour integral 2C to 1C delta cube minus delta W, right. So, you see that we can write, if we subtract equation 1 from equation 2. So, now what, because the interaction of heat and work following path A will get cancelled. Question is, what we can see from this expression? Though del Q and del W, these are path function. So, you understand this quantity del Q minus del W, though del Q and del W they are individually, they are path function individually, but the difference of these two quantities is same whether the path is B or C. So, the important conclusion from this exercise is that though del q and del w, they are inexact differential, because I have written they are not exact differential, because they are not the point function, they are not the property of the system. So, they depends, I mean these two quantities depend on the path through which the process is taking place and the change in pressure and volume following that particular path. So, though these two quantities are path function individually, but difference of these two quantities does not depend on the path, because you can understand del q minus del w following path 2 following path B is equal to following path C. So, these quantities delta cube minus delta w is not the path function. So, though delta q and del w, I mean these two quantities are path function individually, the difference is not the path function, that we can see from this expression. Now, so this is the property of the system and we write it dE. If the difference between these two quantities is not the path function, that means it is a point function, that is the property of the system, and that is how we could write this in the form of the differential, in the differential form, I mean exact differential form to be precise. So, this is d. Now, if we try to write one step further, we can write delta cube equal to dE plus delta w. So, this is perhaps you have studied in your undergraduate course, that is the first law of thermodynamics applied to the control mass system, and when the system is performing a process, the process need not to be a cyclic process. So, this is first law of thermodynamics for the control mass system undergoing any generic or general process. So, today before I complete this lecture, I would like to discuss a few important issues, though those are not, I mean essential for this particular course, but at least I should discuss, because in the first a few lectures I shall try to discuss about the basic, or rather I shall try to recap the conceptual part of the thermodynamics. Why I am discussing? Because this will be very much needed when we will be discussing about different thermal systems, essentially for the quantification of the performance. So, you know that these two are the inexact differential. Why? Because they are path function, while this is exact differential. Right. So, this is the property of the system, because you know nice thing to understand, nice thing to see from here is that though these two quantities are path function individually, but their difference is now the property of the system, right, and that is why we could write it in the form of the exact differential. So, next if we try to write that essentially first law of thermodynamics I am writing first law of thermodynamics at least for this lecture. From the next class onward, I shall simply write first law, second law like this. So, essentially it refers to first law of the thermodynamics. Okay. So, first law of thermodynamics for the control mass system undergoing any general processes. So, this is what we have seen from the last slide, that is delta cube equal to dE plus delta W, right. So, now here E is the total energy. Again from this particular expression I would like to tell you one important thing. See, that means if we go back to the slide, so if you supply certain amount of heat to the system, system has, rather system holds capacity to do some work, right. But try to understand, if we now look at this particular expression, if we supply certain amount of heat, rather certain amount of energy by heat to the system, system has capacity or capability to do some work plus. So, that means all the energy, all the heat which is being supplied to the system is not getting converted into the work. Some part of that energy heat is remaining stored within the system in the form of the total energy. So, this is the total energy, and you know that it can be written in different parts. I mean this is nothing but half mc square plus mgz plus we can write u, that is the one other form. So, let me discuss briefly. So, the total energy, so that is the remaining, it is not possible to have the equal conversion of energy from heat to the work. Remaining energy will be there within the system, and that is nothing but the kinetic energy, potential energy, the form of energy other than these two. So, this is the kinetic energy, this is the potential energy, P E, so this is K E. So, apart from these two different forms of energy, there is another form, and this is known as internal energy. So, this is the form of energy other than the kinetic and potential energy. So, I am writing this is another form of energy other than kinetic energy and potential energy, other than the kinetic energy and potential energy, right. So, this is very important to understand. Now, question is, in most of these, so basically that kinetic energy and potential energy, these two are the microscopic manifestation of the mechanical energy. So, basically this half mc square and mgz, so these two, so that is kinetic energy and potential energy. So, these two are the microscopic manifestation of the mechanical energy. Okay. Whereas this fellow is internal energy, and that is nothing but the intermolecular form of energy due to the molecular rearrangement. I will give you an example. So, this is microscopic manifestation of the mechanical energy, whereas this U is the intermolecular energy essentially due to the molecular rearrangement. Essentially due to molecular rearrangement. Okay. So, basically you can write this total energy in terms of the specific energy, because so this E equal to half m c square plus m g z plus total U. If we try to write specific energy, so this is the total energy and this is specific energy equal to half c square plus g z plus small u. Okay. Now, we have discussed already that potential energy and kinetic energy is the manifestation microscopic manifestation of the mechanical energy, whereas this U, that is the form of energy other than the potential and kinetic energy, is the intermolecular energy, which is essentially due to molecular rearrangement. So, now in most of the thermodynamic processes, if we write it now, I mean we have already derived that first law of thermodynamics applied to the control mass system undergoing any general processes can be written in this form. Now, what is done essentially, if we try to plug in the value of E over here, then we will be getting d of P plus K E plus U plus delta W. In most of the thermodynamic processes, the changes in kinetic and potential energy is neglected. It is not because of the fact that the it is ignored intentionally, rather it is seen that in most of the thermodynamic processes the changes in kinetic and potential energy is negligibly small as compared to the part which is U. So, basically since changes in P and K is neglected in most of the thermodynamic processes, we can write delta cube equal to du plus delta w. So, this is the final form of the first law of thermodynamics for the control mass system undergoing any general process. We could write this form taking this assumptions that the changes in potential and kinetic energy is negligible, and what is mostly true for most of the thermodynamic processes. So, this is the first law of thermodynamics for the control mass system. Now, question is, I told you one important thing, that this fellow is essentially due to the molecular rearrangement. I can give you an example. If you take certain amount of liquid in a container and say the container is like this, container is this, and we are taking say water with a few iron particles. So, this is the container which is containing DI water or any water, and a few iron particles are injected in this liquid. If we have one magnet at the bottom, if we have one magnet at the bottom, say we have one electromagnet EM at the bottom. So, this is electromagnet. If we have the electromagnet, then if we energize this magnet by switching on the circuit, then what will happen? All the particles will move towards the bottom of the container and they will remain stored therein. When they are remaining stored therein, due to the molecular rearrangement of the total substance which is there in the container, energy will be stored therein. If we switch off the circuit and if we deactivated this electromagnet, what will happen? You know that it is because of the stored energy, particles will try to dislodge from their initial positions and they will again slowly come to the original configuration. So, this is the concept of the internal energy. So, basically other form of the potential and kinetic energy, it is because of the molecular rearrangement some energy is stored within the system and that is known as the internal energy. Okay. So, to summarize today's lecture, you know we have discussed about first law of thermodynamics. We have started discussing first law for the control mass system and then we have seen that if the system is control mass system, but if the system is undergoing through a cyclic process, then we could write the equation in the integral form. But since all the processes are not cyclic in reality, we also could establish the first law for the control mass system undergoing any general processes. So, with this I stop here today and we shall continue our discussion on this particular topic in the next class. Thank you.